Okay, so there we have the 8 constants and 8 conditions. Okay, so the final thing we need to do is, and this is where the problem set up. The only thing needs to be done is to lay down these 8 conditions as 8 equations. Okay, so let's do that. It's usually helpful if we can write down theta 1 dot of t, which will be a11 plus 2 times a12t plus 3 times a13t square. Theta 2 dot of t equals a21 plus 2 a22t plus 3 a23t square. Now that we've got those equations for position velocity, we can now sub in the values. So, okay, all set. So, the first condition, theta 1 t equals 0 is a10, which is 0. Theta 1 t equals 1 would give me a10 plus a11 plus a12 plus a13 equals 0.5. Just put t equals 1. Then we have theta 1 dot at t equals 0. So we can refer to this expression, put t equals 0. So we have a11 equals 0. Then we have theta 1 dot at t equals 1. So we put t equals 1 that expression, a11 plus 2a12 plus 3a13 equals 0.2. Okay, next we can go to theta 2. So theta 2 at t equals 1 equals a20 plus a21 plus a22 plus a23 equals 0.5. Theta 2 at t equals 3 equals a20 plus 3 times a21 plus 9 times a22 plus 27 times a23 equals 1. Okay, then the derivative, theta 2 dot at t equals 3 equals, so I put t equals 3 there, a21 plus 6 a22 plus 9 a23 equals 0. Is that right? 3. So 3 is going to be 27. Then theta 2 dot at t equals 1 equals a21 plus 2a22 plus 3a23 equals 0.2. Okay, so so this gives us, well, those 8 equations as 8 conditions, and there are 8 unknowns. So the way you'll solve this is you'll try to write a matrix equation. So you start out all the A's. Let me just do that. Let me Write that down. So what you do is, let's see, so we need 8 rows, 8 columns. Start here. Okay, and then our unknowns are going to be A10, A11, A12, A13, A20, A21, A22, A23 equals something on the right hand side. Okay, so let's just fill it up. So the way this goes is you look at the first equation, it says A10 equals 0. The 0 on the right side means the right hand side will be 0. The A10 would come into picture when you try to assign a coefficient to the first element of the unknown. So that is 1 times A10. And since all of the elements are 0, it will just be zeros for remaining, because the first row gets multiplied with the unknowns, and that should be our first equation. And I'll do it for another one and then just write down the answers. So we have A10, A11, A12, A13. So all those have a coefficient of 1 in front of them, and the right hand side is 0.5. So 0.5 on the right hand side. The coefficients of these first 4 are 1. You just keep doing that. A11 is 0, 0, 1. 0, 1, 2, 3. Okay. 0, 1, 2, 3. And the right hand side is 0.2. Okay, next we go to the next 4 set of equations. We have A20 all the way to A23 equals 0.5. So what I'll do is, those would be the next 4. So it will be 1, 1, 1, 1. Zeros here. And that should be equal to 0.5. Next, we have 1, 3, 9, 27 equals 1. 1, 3, 9, 27. And we have, so remember A20 is the first one. So 0, 1, 6, 27. 0, 1, 6, 27. And that should be a 0. And then final equation is, so 0 for A20, 1 for A21, 2, 3, 1. So 0, 1, 2, 3 equals 0.2. 0, 1, 2, 3. Okay, so this is my grand equation, AX equals B, where A is known, B is known, X is unknown. It's a linear algebraic equation, which you can probably solve it by hand if you want to, but not recommended. So you can solve it by just taking the inverse of A. So 8 cross 8, 8 cross 1, 8 cross 1. So you can compute X. So the X holds the A's. So A10 is 0, A11 is 0, A12 is 1.3, A13 is minus 0.8, A20 is 0.55. A21 is minus 0.375. A22 is 0.4. And then finally, A23 is minus 0.075. It's not very important. The coefficient, the values are not very important. I just got them from writing a Python code, which will give me the answers from that equation Ax equals b. Okay, so I'll show you in a bit Python code. Which does this, which basically computes, I supply A and B, and then it gives me X, and then I do a plot of what the profile will look like as a function of time. So the time, remember, goes from 0 to 3. So 0 to 1, 1 to 3, so 0 to 3. And before I show that, let me just mention this other problem, which is not very different from this one. I just changed one condition. And I will not do this. I'll just maybe put my notes later on. But the problem is similar to this one in the sense that I've specified the position at time t equals 0, 1, and 3. So this up till here, it's the same as the problem I talked about. However, what I did that velocity of joint, the start of motion, that's also same. This is same too. The only change is this condition. So that's the only difference between this problem and so the thing in blue versus this one. So I just changed this condition. Okay, so here I've said the velocity at the intermediate point equals 1 equals the velocity at the second one. So write it down as theta1 dot at 1 should be equal to theta2 dot at 1 should be equal to 0.2. Okay, and that showed up here. Okay. With this problem, everything else remains the same, except that I said the acceleration of the joint intermediate point should be continuous, which means that I now say that theta1 double dot at t equals 1 equals theta2 double dot at t equals 1 should be, well, this should be equal. And then remember that all the other conditions hold true. So I should probably copy paste these. Okay, so we copy them. These are three conditions. This is one condition. Now, it turns out that if the acceleration is continuous, the velocity has to be continuous. And so another condition which I need to add here is theta1 dot at time t equals 1 equals theta2 dot at time t equals 1, even though it's not specified, and that's my 8th condition. So 8 conditions. I need 8 equations. So we have third order polynomial. So you have to set up the problem very similar to the previous case, except that you replace the velocity condition of 0.2 with these two conditions of acceleration is continuous and velocity is continuous. So I'll show you. I did this exercise of computing the A matrix and then the B. Okay, we'll just 2 lines will change, right? Just those conditions, and then everything else will remain the same. So I'll show you code which does that, and there's probably ways to automate even this step, which is I had to handwrite all these equations, including the velocities and so on, but you can actually use the symbolic toolbox to write these expressions, then differentiate with respect to time, use the Jacobian to compute the A matrix and B matrix, and then code which does that problem is let's do it. I don't know if it'll run. Control shift. Okay, so what I did here is I manually copy pasted the A matrix. As I said, you don't have to do this. You can find a better way to do this by writing code for everything I did. You don't need to actually write anything down on paper. You can do this just by using the symbolic toolbox. That's the B. Then I compute X, and that's my solution to the constants. Now I went a step further. I created a time variable from 0 to 1 and 1 to 3. I got the trajectory θ1, θ2, here it is written as Q1, Q2, the velocity, which is the first derivative, the acceleration. So if we run this again, Shift P. And so we get exactly what we coded for. The position is 0 to 1, 0 to 0.5 and 0.5 to 1. The velocity starts and ends at 0, but then there is it's 0.2 at time t equals 1. And if you look at the acceleration, it's not continuous at the start, nor at the end point, nor at the extreme end. Okay, so this is sort of verifying what we did is correct. That is, those constants indeed give the solution as we expected. Here is on the same line. This is code which does the second example. So again, the same thing. I have the A, B, which are hand coded, and then do a plot. Shift P. Okay, here it looks much smoother than the previous one. You can see that the position is smooth there also, but the velocity here is smooth. Acceleration is smooth. The only problem is there's a discontinuity at initial point and the final point, but everything is smooth. So here is how to do this with Python. Now, this is just the start. Once you get this, you need to do the next step, which is you need to get the manipulator to follow that trajectory, and that's what is coming next. How do you control the manipulator to go follow this trajectory? Now, the trajectory, unlike the previous case when we talked about lemniscate or circle, was that we were moving essentially very slow. We were not really concerned about the dynamics of the motion. We were just trying to go plot, 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 but we were not really concerned about going from point A to point B. What if the mass of the robot is high or the inertia is high? Do we account for it or not? So that is something we'll do next.